Section 6.5, the sine and cosine graphs. We've looked at and talked about the sine and cosine functions in terms of the unit circle, and if we think about the quadrantal points, so the points on the x and y axis that make up that unit circle, all I've done is plotted those points and I've connected them with a smooth curve. And so we've talked about what the graph of the sine and cosine look like on the coordinate plane, and there it is again as a refresher. And what we're going to be doing in this section is looking for what the transformations of those graphs are. So if we have y equals a times the sine of b times x plus c plus d, or even if we replace that sine with cosine, what exactly do all those letters do to the graph of the sine function or the cosine function? We're predominantly going to be looking at the sine graph, but the transformations that we are going to talk about happen to both the sine and cosine graph in very similar manners. Therefore, our goal in this section is basically going to be able to make the graphs of these without making a t-chart and plotting points. Let's look first of all at what that a does. If I just have y equals a times the sine of x, a number out in front, what does that a do to the graph? I'd like you to pause the video, and if you can, either on Desmos, so you can use different colors, or on here, or on your graphing calculator, I'd like you to graph each of these four, keep them all on the same graph, and see if you can determine what does that a do to the graph. Although the scale's a little bit different, this is still just our basic sine graph. There you can see I have graphed y equals the 2 times the sine of x. Now I've added y equals 4 times the sine of x. And finally I've added y equals 1/2 times the sine of x. What does that coefficient a do to the front of the graph? It's the amplitude. It's going to tell you how high or how low each peak or valley reaches. So it's the peak amplitude of the graph. Now let's take a look and see what the b does. I'd like you to do the same thing. Pause the video and use either your graphing calculator or Desmos to help you graph these four graphs on your paper. Try to use different colors. Again, to start, here's my basic parent graph of the y equals the sine of x. Here in blue now we have the graph of y equals sine of 2x. Looks like it's getting really messy, but now in purple you can see the graph of y equals the sine of 4x. And now in pink you can see the graph of y equals the sine of 1/2 x. So try to pause the video and take a look and see what does that b do to the graph. Well, in the parent graph, y equals the sine of x, the period is 2 pi. In other words, it repeats itself every 2 pi. So b is going to tell how many periods there are in 2 pi. So if you look at that purple graph, if we were to extend that, there would be 4 sine periods in 2 pi. If you look at the blue one, there would be 2 of them. The way you find the length of the period, therefore, is 2 pi divided by b. And that will tell you the length of one period. Now we're going to look at what happens if we add a number. And so is there a difference between adding the number the sine of x plus 3 or the sine of x plus 3? What I'd like you to do first of all is pause the video again and go back up to this parabola on top and graph the parent graph, y equals x squared, and then remember how it would shift. How would you graph y equals x minus 3 squared plus 2? Let's take a look at that transformation. Hopefully you remember from Algebra 2 that when something is grouped with the x, if I were to take that and set it equal to 0, I get x equals 3, so this is going to shift it right 3, and then this 2 is going to shift it up 2. It's going to be similar with the sine of x plus 3 and the sine of x plus 3. Let's go ahead and graph both of those. Pause the video, and I challenge you to pause the video and graph these on your own without using a graphing calculator or Desmos, just using what you know about the basic sine graph. Again, I'm starting with the parent graph of y equals the sine of x. Here we have the sine of x plus 3, and if you think about it, all it's saying is whatever value you get for the sine of x, so for example we get 1 here, we're just adding 3, so it's going to go up to 4. So it just raises the whole graph 3 units. Now go ahead and graph y equals the sine of x plus 3. And there's the graph of y equals the sine of x plus 3. I graphed the original sine graph, and I simply shifted all of those points on the original sine graph left 3. So that second one, the blue graph, is called the phase shift. It tells you how much the graph is translated horizontally. It's always the value that's grouped with the x. Therefore, the way you're going to find the phase shift is by taking whatever that is after the trig function, and you're going to set it equal to 0, solve for x, and that will tell you how far you're moving it left or right. Now let's go ahead and do two problems. First of all, I'd like you to pause the graph and see if you can simply tell me what is the amplitude, what is the period, and what is the phase shift. Pause the video and do that, and then come back and we'll go through the graphing of this. My amplitude is 3. It's the number that's out in front of the whole expression. My period I find by taking 2 pi divided by b. b, remember, is the coefficient of the x. In this case, it's 2. So 2 pi divided by 2 simplifies to pi. And my phase shift I find by taking that whole big mess after my sine or cosine function, setting it equal to 0, and solving for x. So in this case, I get that my phase shift is negative pi over 4. I'm going to move everything left pi over 4. So the way we're going to graph these, first of all, is going to be to graph everything except for the phase shift. So we're going to base it off of our basic sine graph. We're going to have an amplitude of 3, and instead of having a period of 1 pi or 2 pi, we're going to crunch that all into a period of 1 pi. This isn't my final graph, so I've graphed y equals 3 times the sine of x, and I've just kind of graph them together in a light dashed line. Now I'm going to take each one of these points and I'm going to move it to the left pi over 4 units, which is basically each point that I've plotted there, I'm going to move them all to the left 1 box, because each box is pi over 4. And there in blue you have the final graph. It's a bit misleading because I wrote this in blue, but this blue graph is my final graph of y equals 3 times the sine of 2x plus pi over 2. Now let's try to go ahead and graph a cosine graph. Again, I would like you to pause the video and see if you can write down what the amplitude, what the period, and what the phase shift is. Even though this is a cosine graph, you're still going to find all of those, the amplitude, period, and phase shift, the exact same way you would as though this was a sine graph. So my amplitude is 2. My period I find by 2 pi over b. b is the coefficient of my x, so 2 pi over 3. I can't simplify that at all. And my phase shift, by setting all that mess that's after the cosine equal to 0, I get that my phase shift is pi over 3. So again, we're going to start by graphing the kind of the parent graph of y equals 2 times the cosine of 3x. And then from there, we're going to do our phase shift of pi over 3. Here you can see I have 2 times the cosine of 3x. My period is from 0 to 2 pi over 3, and I go to a height of 2. Now I'm going to shift all of those points to the right pi over 3 units. And there in the purple is the final graph of y equals 2 times the cosine of 3x minus pi. Please come to class if you have any questions on any of these translations or transformations, and we can go over some more examples.